We learned about the concept of applying approximating rectangles to get an approximation for the area under a curve. What we want to do now is see, how do I formally figure out this definition of the area under a curve? And we're going to relate that to what we call Riemann sums, which is essentially what we just did, and also definite integrals. So we've seen the indefinite integral to represent the antiderivative. Definite is going to basically be their bounds. So I'm going to start from some x value, end at some x value. So first and foremost, we're going to go through the definition of a definite integral. And it tells us if a function f is defined for some x values between a and b, we can divide the interval from a to b into n subintervals of equal width. And that equal width is delta x. It's the length of the interval divided by n. We're going to let x0 be the first endpoint, which is a, then x1, x2, x3, and you keep going into the last value, xn, which is b. These are the endpoints of the subintervals. And x1 star, x2 star, all the way up to xn star are going to be the sample points we pick in those subintervals. So if I want to figure out the true area under a curve, remember we're going to take the limit as n approaches infinity of the sum of those approximating rectangles. This is exactly what the definite integral of a function is from a to b. So what we're going to do is we're going to put our function inside that integral. The bounds from a to b are going to indicate what values x is changing between. So this is going to give me the area under the curve, f of x, from a to b. In terms of our definition, it is the limit as n approaches infinity of the sum from I equals 1 to n of the height of our rectangles, which is where we evaluate the function at our sample point, times that width, which is delta x. Of course, provided this limit exists, and gives you the same exact value regardless of the sample point you choose. If you can do this, we say that function is integrable over this interval from a to b. So we've seen how this integral without the bounds is representing taking an antiderivative. Really, each part of this definite integral has a specific name. So we're going to dissect this piece by piece. The value up here is called our upper limit. So it's where we stop finding the area. And so likewise, this one is called our lower limit. Let me write it down here. This symbol is our integral sign. So it's kind of standing for sum. You're taking the sum of those things. And the thing on the inside is called our integrand. That dx is, again, that differential. It's standing for a change in x. Another thing you might hear is that these values of a and b, which are the upper and lower limits, they're often called limits of integration. So it's where you're finding the area underneath. This sum, because it's ending at a value n, is called a Riemann sum. So Riemann is just the name of a mathematician. He was the one that kind of first came up with all of these pieces. So any of these types of sums are called Riemann sums. So we really want functions to have area under the curve, but unfortunately not all functions are going to be integrable. So I'm not going to be able to find the area. But if you do have a function that's continuous over that interval, or even if it has discontinuities, like if it jumps up at one point, you can still find the area as long as there's a finite number of them. And then really when we're trying to calculate this to begin with, we're going to use that right endpoint to evaluate the sum. Because I've got to go through this limit definition, just like we did when we were dealing with derivatives. You've got to see where this stuff comes from before you get to handle the shortcuts. So in the next section, we're going to relate the definite integral to that antiderivative. But before we can get there, we want to go through this definition of an integral. But luckily, we can pick any sample point we want. We're going to just choose the right endpoints to calculate those. So there is a theorem, if a function is integrable, Then if you want to find the area under that curve from A to B, it is the limit as n approaches infinity of that Riemann sum, specifically where that xi, or the sample point you're picking, is the right endpoint. So delta x is still just the width of each subinterval. So let's try an example. We've got a function, which is a nice parabola, x squared minus 2x. We've got an interval from 0 to 3. We're going to evaluate this with 3 rectangles, and then we're going to go ahead and go through a formal definition to find the area under the curve from 0 to 3. So first and foremost, if you want to consider graphing these, you can take your time to plot this, but both of them have an x in common, so you can factor that out. So if you plug in 0, you're going to go through the x-axis. If you plug in 2, you're going to go through the x-axis. So you really have a nice parabola. It opens upwards. Okay. If I want to approximate this with 3 subintervals, that would be n equals 3. My intervals from 0 to 3, so the width of my rectangles is delta x. It's the length of my interval, which is 3, divided by the number of rectangles, which is 3. So each and every rectangle is going to have width 1. And so my right endpoints on this interval from 0 to 3 would be 1, 2, and 3. So our subintervals are from 0 to 1, from 1 to 2, 2 to 3. So my right endpoints are these values. So the Riemann sum is R3 for the right endpoints. We'll sum up from I equals 1 to 3, plug those right endpoints into the function, and times it by the width of those rectangles. So I plug in my first right endpoint, which is 1, to get the height of my rectangle, times it by that width, delta x. On the second subinterval, I plug in 2, times it by delta x. And on the third subinterval, my right endpoint is 3, I times it by delta x. So all of these values I want to plug into this function to get those heights. If you plug in positive 1, you're going to go through negative 1. If you plug in 2, you're going to go through 0, so your height is 0. And if you plug 3 into this function, you're going to see that your height is going to be 3, and for all of them, your width is going to be 1. So ultimately, this Riemann sum will tell you that the area under this curve from 0 to 3 is going to be 2. Now we get to the fun part. To actually evaluate this definite integral, I've got to go through the limit of that Riemann sum. So we're going to evaluate this Riemann sum first. And so I've got to come up with, what does the expression for delta x look like? What does the expression for my right endpoints look like? So with n subintervals, our delta x is still the length of my interval, which is 3, divided by the number of subintervals. And in this case, that's n. So delta x is going to equal 3 over n. Our right endpoints, remember, are xi. You start at your value of a, and you add to it I times delta x. In our case, the very first value we start at is 0. So this is equal to 0 plus I times delta x, which is 3 over n. So ultimately, the right endpoints can be given by 3I over n. So if I want to evaluate this expression, I need to, instead of using my right endpoints, plug in this expression 3I over n, and delta x is 3 over n. Okay? So this is going to give me, for an arbitrary amount of intervals, I'm picking n of them, this will be the area of those rectangles over the interval from 0 to 3. And they're going to be equal width rectangles, with that width being 3 over n. Okay? Because afterwards then I'm going to let the number of rectangles approach infinity to give me my true area. So what I'm going to do is I'm going to plug 3I over n into this function, x squared minus 2x. So this is equal to our sum. We get the input squared minus 2 times the input, and then times our delta x. So simplifying those pieces, 3i over n squared is going to be 9i squared over n squared. And then 2 times 3 will give you just a 6, and the I over n stays. And then this is still times delta x. So if I go ahead and distribute this into both pieces, that's going to be our sum. We're going to get 27i squared over n cubed minus 18i over n squared. Okay? And so I want to come up with kind of a clean-cut expression for this. So what I'm going to do is split these summations. So I'm going to take the sum of the one minus the sum of the other. And what you can really think is, again, this is I that's changing. So these n's in the 27, the n's in the 18, those are really just constants in terms of this summation. So we can go ahead and pop out that 27 over n cubed. We can pop out the 18 over n squared. And then we're left with the sum from I equals 1 to n of I squared and the sum from I equals 1 to n of I. And these are exactly the formulas that we just went over. So this is equal to 27 over n cubed. If I sum up I squared from 1 to n, it's n times n plus 1 times 2n plus 1 over 6. Likewise, if I sum up I from 1 to n, it's n times n plus 1 over 2. And then we can do a little bit of simplification. 27 over 6, they're both divisible by 3. So that would be 2 and a 9. Likewise here, both divisible by 2. So this would be 9 and 1. So ultimately, if you go ahead and just distribute that 9, you'd get 9 times n plus 1 times 2n plus 1. In the bottom, you've got 2n cubed. And for that second expression, it's 9n times n plus 1 over n squared. So again, what this tells you is over the interval from 0 to 3 for this function, if I take 100 subintervals, I would plug in 100 here, and that would tell me the area of my approximating rectangles. If I take 1,000,000 subintervals, I would plug in 1,000,000 for n, and that gives me the sum for all of those rectangles. Okay? To find my true area, I want this number of rectangles to go to infinity. So the integral from 0 to 3 of our function, which is the integral from 0 to 3 of x squared minus 2x dx, based on this limit definition, is the limit as n goes to infinity of the sum of those approximating rectangles. And we have now figured out a nice expression for those approximating rectangles. So in place, I'm going to put exactly this nice expression we just came up with. So we're going to plug that in for that sum. And all that's left now is I need to take a limit as n goes to infinity. So I really have got to do some type of algebra manipulation to make this a little bit cleaner. You can FOIL the n plus 1 times 2n plus 1 and then distribute 9n to it. So ultimately, if you do that, you would get 18n cubed, 27n squared, 9n, bottom stays untouched. This one's not so bad to distribute out. So that would be 9n squared plus 9n over n squared. Okay. So for both of these, unfortunately, we have that indeterminate form because I'm approaching infinity. So what we need to do is divide top and bottom by the highest power in the bottom. So really the top is going to get multiplied by 1 over n cubed, and same thing in the bottom. So I'm going to take every piece and divide it by n cubed. For this term, n squared is the highest power in my denominator. So I'm going to go ahead and divide the bottom by n squared, but that means we need to do exactly the same thing in the numerator, so I don't change my expression. Okay. So if we go through that, if you distribute and divide all of these by n cubed, 18n cubed over n cubed will be 18. 27n squared over n cubed leaves you with an n in the bottom. And 9n over n cubed is going to leave you with an n squared in the bottom. And then 2 is going to be what's left in the denominator because n cubed over n cubed is going to disappear. For our second expression, when you divide everything by n squared, you're left with 9 plus 9 over n in the top, 1 in the bottom, and now you have no problems letting this go to infinity. So as n goes to infinity, this goes to 0. As n goes to infinity, that goes to 0. This goes to 0. My bottom is 1 there. So ultimately, my first piece goes to 18 over 2. My second piece goes to 9 over 1. 18 over 2 is 9, minus 9. That tells me the area under this curve is going to be 0. So this process is definitely really tedious. We're going to learn another method that relates the antiderivative to the area in the very next section. But you do want to get some practice trying this out because it is an important process to understand where this comes from. Okay. Let's try some more examples though. Let's evaluate the following integral by interpreting it in terms of area. So we want to integrate from 0 to 10 of the absolute value of x minus 5 with respect to x. So let's think about this function we're dealing with. Remember our absolute value function's piecewise. You're going to get exactly the thing inside if the thing inside is greater than or equal to 0. You get the opposite sign if the thing inside is less than 0. So if you were to distribute that out, the minuses would cancel in the second piece for the minus 5. And if you add the 5 over for both of these expressions, this will give you x minus 5 if x is greater than or equal to 5, negative x plus 5 if x is less than 5. Okay. Really, this is just the absolute value function that's been shifted to the right 5. So if you think of the graph of that, it's got that V shape, and it has its point at 5, 0 instead. So we want to find the area under this curve from 0 to 10. So really, I'm looking for the area here plus the area here. And that's really just two triangles. So I don't need to go through this limit definition. It's the area of two triangles. The base is going to be 5 and the height is going to be 5. So ultimately, this definite integral is 1/2 base times height for the first triangle plus 1/2 base times height for the second triangle. So ultimately, the area is just 25. Let's try another example doing the same kind of thing. We're going to evaluate this integral by interpreting it in terms of area. This one's a little bit harder because that function's not as clear-cut as to what it is. But I know I'm just going to take my x values between -3 and 0. What I want to do is I'm going to set that inside equal to y because it's really my function. Y equals this function. If you subtract the 1, you'll get y minus 1 is equal to the square root of 9 minus x squared. And I don't like this square root, so let's go ahead and square both sides to get rid of it. And so that gives us y minus 1 squared is equal to 9 minus x squared. Well, if I add the x squared over, that gives me a circle. Now, the only stipulation is it's not quite a circle because that's not a function. And this thing is a function on the inside. So I've got to dive in a little bit deeper as to what this looks like. So what you want to think is that y minus 1 is the square root of 9 minus x squared. Anytime you take the square root of something, you're going to get a non-negative number. So ultimately, y minus 1 is greater than or equal to 0. So this really is only true for y being greater than or equal to 1. So it's kind of like I'm not getting the full circle. I'm only getting the top half of the circle. Like this would be a circle centered at 0, 1 with radius 3. But instead, it is now a semicircle centered at 0, 1 with radius 3. So if we go ahead and graph that, it would be like your circle is centered right here at 0, 1 with a radius of 3. So you'd go up 3, left 3, right 3, down 3. But I'm only getting this top half because y is greater than or equal to 1. And in reality, I'm only finding the area from 0 to 3, so I don't even need all of this. I only need this portion here. So I want to find the area under this curve from -3 to 0. So the piece I'm looking for is this area here. In terms of geometry, you can split this up. So if we dissect it, this is really going to be a quarter of a circle. So this top half we can call A1. This bottom half we can call A2. A1 is a quarter of a circle. So the area of A1 is 1/4 pi r squared. Well, my radius is 3, so this is 1/2 pi times 9. The area of that semicircle or quarter circle is 9 pi over 4. My bottom piece that I've basically attached to it is a rectangle, and the area of that rectangle has width 3, height 1, so its area is 3. So ultimately, this integral that I'm searching for is going to be the first area, 9 pi over 4, plus 3. So now that we've got a little bit of interpretation, let's consider some properties that these definite integrals have. We're going to look at just one of them kind of in detail. The rest of them we're not going to go through in the same manner. But we pretty much defined the integral assuming that the lower bound is smaller than the upper bound. But it really makes sense if you have the reverse case. So kind of like you're finding the area in the back way. So if we reverse the roles of A and B, then delta x changes from B minus A over n to A minus B over n, which is really the negation of the previous delta x we had. So all that happens is if I'm finding the integral from A to B, or the area under this curve from A to B, it's going to change signs if I trace it out in the backwards direction. The other one that's a little bit easy to see is if your A is equal to B. So you're finding the area really under a point. That doesn't have a second dimension of it, so that change in x is 0. The area under a curve under a single point is nothing because there's no width to it. Okay. So we have tons of properties. That's just a sneak peek at 2 of them. The first property is exactly this. If I find the area under a curve from A to B of a function, it's the exact opposite of the area under the curve from B to A. So you're tracing it out in the opposite direction. If I find the area under a curve from A to A, that has no area. If I find the area from A to B of a constant C, we can go ahead and kind of draw a little picture over here. You have a constant function C from A to B. You're really just creating a rectangle. The height of this rectangle is exactly C, and the width is B minus A. So the area under a constant function is going to be C times the length of the interval B minus A. Okay. If I want to add or subtract 2 functions inside my definite integral, you can go ahead and take the area under the one and add or subtract the area under the other. If I have a constant inside my definite integral, just like with antiderivatives, the constant pops out. You can pop the constant out and take the area of the thing left over, or the definite integral left over. If I go ahead and find the area under a function from A to B, and then find the area from B to C, it's exactly the same thing as finding the area from A to C. So this one you can kind of read in a couple different directions. If I start with an integral, I can split it up. with some point in between the two. Or I can go ahead and condense these two to a single integral. So again, pictorially, I'm starting at A and I'm ending at C. If I chop it up in the middle at this point B, and I look at the area from A to B, that would be this first integral here. And then if I find the area from B to C, that would be the second integral here. Overall, it still gives me this entire shaded region from A to C. Okay. Seventh property is if your function is non-negative over an interval, the area underneath it better be non-negative. If you have one function is bigger than another over an interval, the area under the bigger function is going to be more than the area under the smaller function. Okay. If you know your function is trapped between two values, little m and capital M, over some interval, then kind of applying this exact same rule, your function is trapped between the area under each of those two other ones. But since those are both constant, it's equal to the constant times the length of the interval. Constant times the length of the interval. So you'll know exactly what your area is trapped between. So let's try an example utilizing these properties. If we know the area under the curve from 1 to 5 is 12, and from 4 to 5 it's 7, we want to find the area from 1 to 4. And this is where we're going to use the property that you can take some interval and split it up. So if I look at the integral from 1 to 5 of a function, it's the same thing as finding the area from 1 to 4 and then from 4 to 5. And plugging in the two pieces we know, the area from 1 to 5 is 12. We don't know this middle piece, it's what we're searching for, but the area from 4 to 5 is 7. So if I want to solve for my unknown quantity, I just go ahead and subtract 7 from both sides. So 5 is going to be the area of the function from the interval on 1 to 4.